Someone in the meeting room at NASA's Johnson Space Center looked at the data from the recovered Artemis I capsule and said the words that nobody in that room wanted to hear out loud. The heat shield failed. Not catastrophically, not in a way that killed anyone because there was no one on board to kill, but failed in a way that was real, documented, photographed, and impossible to explain away. More than 100 locations across the 16.5-foot surface showed damage that the engineers had not predicted, had not modeled, and did not fully understand. Chunks of the protective material had sheared off, not because they were designed to, because something had gone wrong inside the shield itself, something that the equations hadn't accounted for, something that had built up pressure in places pressure was never supposed to build, and then blown outward, carrying pieces of the only barrier between a crew and 5,000-degree heat into the slipstream behind the capsule. That was December of 2022. Artemis II launched with 4 human beings on board in April of 2026, with the same heat shield design, the same material, the same formulation that had already shown, in the most unambiguous way physics allows, that it could fail. NASA knew, they launched anyway, and the question of why is not the simple one. It is a question about institutions and timelines and risk tolerance and the specific, very human calculation that gets made when the cost of caution is measured against the cost of delay. It is a question about what we are willing to accept when the destination is the moon and the schedule is already years behind. And it is a question that, depending on how April 10th had gone, would either be forgotten entirely or would define the agency for a generation. This is the story of that decision, how it was made, what it was based on, and what it says about the relationship between human ambition and the physics that human ambition has to answer to eventually, whether it wants to or not. The Avcoat material that makes up the Orion heat shield is not new. It is a descendant of the same substance that protected the Apollo capsules when they came home from the moon in the late 1960s and early 1970s. Those missions worked. The material worked. The Apollo program returned 12 astronauts from lunar distance re-entries without a single heat shield failure, and that track record was part of the foundation on which the Orion program was built. If Avcoat worked for Apollo, the reasoning went, a modernized version would work for Artemis. The engineers updated the formulation slightly, made adjustments for manufacturing improvements, for material availability, for performance optimization. Small changes, reasonable changes, the kind of changes that get made in any engineering program across decades of development without anyone considering them a fundamental redesign. But here's the problem. The small change to the Avcoat formulation affected something that nobody caught until it was too late to catch it cleanly. It affected the material's permeability, its ability to breathe. During a re-entry, as the outer layer of the heat shield heats to thousands of degrees and begins to char, gases are generated inside the material. Those gases need somewhere to go. In the Apollo-era Avcoat, they vented through the outer char layer without difficulty, escaping harmlessly into the slipstream. In the reformulated Avcoat used on Orion, the permeability was different. The outer layer, under certain thermal conditions, became less permeable than the gases building behind it required. The pressure built. And when the capsule performed its skip re-entry, dipping into the atmosphere to shed velocity, then briefly climbing back out before the final descent up by Fiumicot. The outer char layer cooled slightly while the internal pressure remained, and when the capsule descended again and the heating resumed, the pressure that had built in the cooler phase had nowhere to go. The char layer cracked, chunks blew off, not everywhere, not all at once, but in more than 100 places, the shield had not behaved the way any model said it should. The engineers who examined the recovered Artemis I heat shield spent 2 years trying to understand exactly what had happened and exactly why. They ran tests in arc jet facilities, the specialized labs that can generate the kind of heat a re-entry produces in a controlled environment. They sent samples to wind tunnels, to laser heating rigs, to materials analysis labs at multiple NASA centers. They built computer models incorporating what they had learned and ran them against the failure data. And they reached the conclusion that they believed, with the confidence that comes from 2 years of intensive investigation, explained the root cause and pointed toward a solution. The solution was not a new heat shield. The solution was a modified trajectory. And this is where things change. The reasoning was precise and From an engineering standpoint, defensible. The damage on Artemis I had occurred during the skip phase of re-entry, during the specific thermal conditions of the climb back out of the atmosphere, when the external temperature dropped while the internal pressure remained elevated. If they eliminated that particular thermal profile, if they modified the re-entry trajectory so the capsule stayed in the atmosphere longer on its initial dip and came back out with less dramatic temperature swings, the outer char layer would remain permeable throughout, the gases would vent as intended, the pressure would not build, the chunks would not blow, the same heat shield, flown on a different path, would perform correctly. This was the bet. Not a reckless bet. Not an ignorant bet. A calculated bet. Made by serious engineers with serious data, based on a serious investigation that had cost 2 years and resources that would be difficult to quantify. The bet was that they understood the failure well enough to engineer around it without replacing the part that had failed. But it gets worse. Not everyone believed the bet was sound. Charles Camarda, a former NASA astronaut who flew on Space Shuttle Discovery and spent years as an engineer inside the agency, reviewed the analysis and reached a different conclusion. He said publicly, in interviews, in written statements, before Artemis II ever left the launch pad, that NASA did not fully understand the root cause of the Artemis I heat shield damage, that the tests they had conducted could not fully replicate the conditions of an actual re-entry, that the models they had built were based on incomplete physics, that the trajectory modification was an engineering judgment made in the presence of uncertainty that had not been fully resolved, and that flying 4 human beings behind this heat shield, under these circumstances, was a mistake. Not a bureaucratic mistake, a life safety mistake. The kind that gets investigated after the fact, slowly, by people who have to explain to families why the risk assessment said acceptable when the outcome said otherwise. NASA heard him, reviewed his concerns, brought in outside experts to evaluate the analysis independently, and then proceeded with the mission as planned. The agency's position was that the investigation had been thorough, the root cause was understood well enough to mitigate, and the trajectory modification addressed the mechanism of failure that the data pointed to. The position was stated with the calm institutional confidence that large technical organizations project when they have made a decision and are committed to it. The kind of confidence that, in the history of human spaceflight, has sometimes been exactly right and has sometimes been the last public statement before something goes irreversibly wrong. The launch was April 1st, 2026, but that's not even the worst part. The worst part is the institutional logic that made all of this feel not just acceptable but necessary. Replacing the Artemis II heat shield with the redesigned version NASA had already ordered for future missions would have required removing the one already installed, recertifying the capsule, reprocessing the vehicle, and delaying the launch by 18 months or more. 18 months was not just a schedule number, it was a budget number, a political number, a number that had implications for the program's funding, for the agency's relationships with Congress, for the contracts and jobs and institutional commitments that a program of this scale generates and depends on. The Artemis program had already been delayed for years. The original target for a crewed lunar flyby had been 2023. It had slipped to 2024, then 2025, then early 2026, then April of 2026 after multiple scrubs. Every delay had cost money and credibility and the specific kind of political goodwill that space programs require to survive long enough to accomplish anything. The calculation NASA made was not reckless in the way that word implies carelessness. It was a rational response to a system of pressures that reward moving forward and penalize stopping. The heat shield data said there was a problem. The engineering analysis said the problem was understood and addressable without replacement. And outside critics said the analysis was insufficient. 2 of those 3 things pointed toward launching. 1 pointed toward waiting. And in institutions that measure time and budget, cycles, and political administrations, the weight given to each of those inputs is never purely technical. This is what spaceflight actually is, not the clean, heroic, well-lit version that press conferences present. Not the image of 4 astronauts walking to the pad in matching suits with the American flag behind them and certainty in their eyes. The actual thing, which is a continuous negotiation between what we know and what we don't, between what the physics demands and what the schedule allows, between the confidence of the people who built the thing and the doubt of the people who question whether the confidence is warranted. Every crewed mission in history has been this negotiation. Most of them have come out on the right side. Some of them have not. The Challenger crew was told the O-ring concerns had been addressed. The Columbia crew flew a mission where foam strike risk had been assessed as acceptable. The specific mechanism of failure was different each time. The institutional logic that produced the decision to fly was not. And this is where the story of the Artemis II heat shield stops being about materials science and becomes about something else, about the specific human capacity to look at incomplete information and construct confidence from it. To take a 2-year investigation, a modified trajectory, and a simulation that cannot fully replicate the conditions it is modeling, and arrive at a number, a probability, a risk assessment, an acceptable margin, and then sign the form that says fly. Not because the uncertainty is gone, because the uncertainty has been named, and named uncertainty is easier to manage than the unnamed kind, even when the naming does not actually reduce the risk. 4 people got into integrity on April 1st, 2026, knowing all of this. Not in the abstract way that all astronauts know risk is inherent in what they do. In the specific way that comes from being briefed on the Artemis I heat shield damage, on Camarda's objections, on the trajectory modification, and what it was designed to address and what it could not guarantee. They read the reports, they attended the reviews. They asked the questions that people ask when they are trying to decide whether the people who built the thing they are about to trust with their lives have gotten it right, and then they got in the capsule. On April 10th, at 4:14 in the morning Pacific time, the signal from integrity disappeared into the plasma of re-entry. For 13 minutes, nobody knew. At 4:27, the signal returned. The heat shield had held. The trajectory modification had worked. The bet had paid. The capsule splashed down in the Pacific off the coast of San Diego, and 4 human beings stepped out into the morning air and breathed it, and the press conferences happened. And the word historic was used many times, and the images of the crew on the recovery ship were warm and genuine and deserved. And the heat shield was pulled off the recovered capsule and sent to engineers who are currently examining it to determine how it performed, whether the damage was within acceptable parameters,